Hi folks, this is our extra calorimetry problem number 1. It reads a mass of zinc that is 110.53 grams with a specific heat for zinc of 0.3879 joules per gram degree Celsius is heated to 100 degrees Celsius in boiling water, and 100 has 4 significant figures, 100.0. It was placed into a calorimeter with a mass of 7.00 grams with a specific heat of 1.40 joules per gram degree Celsius, containing water of a temperature of 24.0 degrees Celsius. Once the contents reach equilibrium, the temperature is 26.0 degrees Celsius. What is the mass of the water in the calorimeter? Ignore the calorimeter and recalculate your answer to find the mass of the water again. That should help us see how much effect the calorimeter has on the problem. So first, what do we know? What do we know about the metal? What do we know about the water? What do we know about the calorimeter? So first off, we'll make a chart. Always make a chart when you do calorimetry problems. I have Q, which is heat. A negative value for Q would be losing heat, and positive value would be gaining heat. M is for mass, C is for specific heat. Delta T is the change in temperature. T sub F would be the final temperature, and T sub 0 the initial temperature. Delta T, the change in temperature, is simply the initial temperature subtracted from the final temperature. So T sub F minus T sub 0. Okay, so if we read through our problem, we would see that it gave us the mass of the zinc, 110.53 grams. Keeping your units, like grams, is very important. Always keep them in the problem. Oh man, and of course I put that in the wrong column. 110.53 grams. We don't know the heat of the metal yet, the heat change of the metal. C, the specific heat of the metal. We are told the metal is zinc. Specific heat of zinc is 0.3879, and our unit joule per gram degree Celsius. It tells us that the metal was initially heated to a temperature of 100.0 degrees Celsius in boiling water, which we know will never get above 100.0 degrees Celsius at standard altitude, room conditions, that kind of thing. And we'll learn more about that later this year. It tells us that when the experiment is completed and the calorimeter, the water, and the metal have all reached an equilibrium temperature, they're all, of course, at that point the same temperature. That is 26.0 degrees Celsius. The temperature, final temperature for the metal and the water and the calorimeter are always the same. Your goal at the end of a calorimetry experiment is to have all of your components come to the same temperature. And then you know the experiment's done. So we can calculate our change in temperature by taking 26.0 degrees Celsius and subtracting 100.0 degrees Celsius. That'll give us a negative value for change in temperature. Obviously our metal is very hot at the beginning. It goes into the water, and heat moves from the hot metal to area of lower temperature, in this case the water. So the metal will be losing heat to the water. So our change in temperature is a negative 74.0 degrees Celsius, which is 26.0 minus 100.0. And when we add and subtract, remember our significant figures both come in the tenths place of these two numbers, so we are significant also to the tenths place here. What do we know about our water at the beginning of the experiment? Our whole goal in this problem is to find the mass of our water. We know that the specific heat of water is 4.184 joules per gram degree Celsius. value you need to memorize. We also know that at the beginning of the experiment, before the hot metal was added, the water was at 24.0 degrees Celsius, and that's given in the problem. So we can also calculate our change in temperature for the water, our final temperature minus our initial temperature, which gives us a value 26 minus 24 of 2.0, also significant to the 10th place, degrees Celsius, 2.0 degrees Celsius. For a calorimeter, we're given in the problem that the mass of our calorimeter is 7.00 grams. We're also told that the specific heat of our calorimeter, which happens to be styrofoam, is 1.40 joules per gram degrees Celsius. And we know that our calorimeter and our water have to be the same temperature at all times. So we are also going to have a change in temperature for the calorimeter of 2.0 degrees Celsius, just like for the water. If the calorimeter contains the water, we're assuming they're the same temperature because we can't stick a thermometer into the styrofoam without puncturing it and making it useless. So now that we have all of this information, it looks like we would be able to use our calorimetry equation, Q equals M times C times delta T, to find the heat lost by the metal and also the heat gained by the calorimeter. So first we'll calculate for metal. We want to find the Q of the metal. We're going to find that that is equal to the mass of the metal, 110.53 grams, times the specific heat of this particular metal, 0.3879 joules per gram degree Celsius, that's zinc, times delta T, which in this case, since the metal lost heat to the water, it had a change in temperature of negative 74.0 degrees Celsius. If we type that all into our calculator, remember, as we're multiplying or dividing through a problem, in this case we're multiplying these three, we find we have 5 significant figures in this, 4 here, and 3 here. So our answer can only contain the smallest of those numbers, 3 significant figures. So if we type that into a calculator, we would find that the heat lost by the metal would be negative, since it's losing heat, 3,170 joules, and that is 3 significant figures, because if you have a 0 here in the ones place, that would not be significant. So I can put here a negative 3,170 joules. That's the heat that the metal lost. So maybe we'll erase just to save some space here. I could also find the heat that the calorimeter gained in exactly the same way. Heat is equal to mass times specific heat times change in temperature. So our heat for the calorimeter will be the mass, 7.00 grams, times the specific heat, 1.40 joules per gram degrees Celsius, times our change in temperature, which is going to be 2.0 degrees Celsius. If we type that into our calculator, we would find that we can only have 2 significant figures. Q for the calorimeter is going to be 20 joules. Both of these figures need to be significant, the 2 and the 0, to give us the 2 significant figures that we can have. So we can't write 20 joules this way because that would only have 1. So we'd have to use scientific notation in this particular case to denote that both the digits are significant, the 2 and the 0. So 20 is actually 2 times 10, 2.0 times 10 to the first joules, which that really means 20, 2.0 times 10 to the first joules. Now, the only things I don't know are the mass of the water, which is my goal, and the heat that the water gained, which I obviously am going to have to find. which isn't hard because we also know, according to our calorimetry theory, that all of the heat that the metal lost is going to be gained by the water and the calorimeter, right? We can't, in a calorimetry situation, our goal is to not allow heat to be lost or gained from the surroundings. Our styrofoam calorimeter is, we hope, sufficient to insulate our experiment from the outside world, keeping all the heat contained. So any heat that the metal loses must be gained only by the system itself, the water and the calorimeter. So the negative heat of the metal, well, the metal is already negative. So if we want the negative, then we have to make it positive. That is a confusing point there, but if we want the negative heat of the metal and the thing is already negative, then we just want to make that a positive. So the negative of the value of the heat of the metal would be a positive, is equal to the heat of the water, which we don't know yet, plus the heat of the calorimeter, which we know to be, and I'm just going to write 20 joules here, and I'm going to make a little underline to show myself that those are two significant figures. We have significance in the ones place here. So if I were to solve for the heat of the water, I would subtract this 20 from both sides. I would be significant in the ones place here, but not here. This is only 3 significant figures, so this isn't. So I'm only going to be able, when I subtract, to keep significance in the tens place here. So I would have the Q of the water equal to 3,150 joules, which is a positive value, which I can add in here, 3,150 joules. Alright, so now I want to find the mass of the water. Well, the exact same equation I've been using. Q of the water equals mass of the water times specific heat of the water times change in temperature for the water. I know lots of people like to solve for the variable we're interested in. So if I did that first, I would find the mass of the water is equal to the heat that the water gained, Q, divided by C times delta T. Then I could just plug in, solve for M, which I'll just keep going here. Q of the water we know to be 3,150 joules, divided by the specific heat of the water, 4.184 joules per gram degree Celsius, times the change in temperature for the water, which we find to be 2.0 degrees Celsius. So if I type this into my calculator, and I see that my units cancel, joules cancel with joules, degrees Celsius with degrees Celsius, then I have a gram here in the denominator of the denominator, which makes it a numerator value. So mass in grams, that works out really well. That's what we want. And if I type all that in, then I would find the mass in grams of the water to be 380 grams. Now this is 2 significant figures because I can only keep 2 due to the 2 significant figures in the temperature value. So I would find my mass of water to be 380 grams, 2 significant figures there. So that's the solution of my problem, but then it asked me to go on and also solve for the problem if I ignored the calorimeter. So in this case I would just ignore the calorimeter. If I do that, then I would find that the heat lost by the metal can only be equal to the heat gained by the water. In that case, the heat lost by the metal would be 3,170 joules. And then Q of the water, I don't have, I can't count on what I solved for because we haven't done that part yet. If we go back and ignore the calorimeter, so I can say I don't know the mass of the water, but I do know the specific heat of the water, which would be 4.184 joules per gram degrees Celsius, and I do know the temperature change for the water, 2.0 degrees Celsius. So here I would, so Q of the water is equal to mc delta T for the water, which I just substituted in here. Then I would solve for the mass of the water by dividing 3,170 joules, 3 significant figures there, by 4.184 joules per gram degrees Celsius times 2.0 degrees Celsius. I would also, once I type that into my calculator and rounded to my 2 significant figures due to having 2 in the temperature reading, I would also come up with an answer of 380, oops, not that, grams. So my answer actually has not changed at all if I ignore the calorimeter. This shows us that significant figures cause the calorimeter to effectively be canceled out of calorimetry problems oftentimes because the specific heat is fairly high, the calorimeter is fairly light, and the temperature change it experiences is small. This causes it to be such a small value that it actually cancels out just due to rounding by significant figures in many cases. So that might help you out with the lab report that you are writing right now also. And I will record calorimetry problem number 2 soon, and I hope that that gives you a little bit more experience with maybe the hardest math that you've seen thus far in chemistry. Hope you're having a good night. Goodbye.